semiconductors, we use oxide to prevent the interference between two electrical elements. For example, the lead shop. Lead shop means that in the CMOS, there would be the fringing, the bypass currents would be exist below the channels. So we have to cut off this fringing electric field. So we used to use this local oxidation of silicons. However, the locals had the limitations because it could only block the surface near the surface of the silicons. Also, there will be a due to bird's beak, we cannot use effectively on the wafer. And nowadays we use these trench implantations or STI or DTI. We first etch the trench with the anisotropic etch method, and then we used to deposit the polysilicon to prevent collapsing on to prevent the falling down between the edged trench. If we let those area with the vacuum, then the wafer could be damaged. So we fill up with the polysilicons or silicon nitride, like oxide. And then after we deposit the oxide, we flatten the surface for the next fabrication process. And then we're going to find out how we deposit the oxide. First, there are two ways, like wet etching, dry etching. There are thermal oxidations and the oxide. First, let's see thermal oxidations. The thermal oxidations is used for gate dielectric on fins, and the locos or steep shallow trench implant or ILD, the interlayer dielectric on the 3D structures like and NAND flash. And if we using the silicon dioxide has several advantages. First, the material is similar to the silicon, so it has so good diffusion. It can work as good diffusion mask, and it can has very good etching selectivity between silicon and silicon dioxide. And most of all, it has very good, excellent electrical insulator because it has an energy band gap of 9 electron volts. And also, if we well orient the silicon dioxide, if we grow well, then it also has a high breakdown electric field. The benefit of getting a high breakdown electric field has the is very important for scaling down, because as the gate length or gate width or contacts are scaled down, then by the law of electric field, which means the potential over the distance, as we scale down, then distance would be go lower, then the electric field would be much get higher. So there is a in thermal oxidation, there are two ways. First of all, a dry oxidation and wet oxidation. Those two ways are similar. The first, the dry oxidation uses oxygen gas, and the wet oxidations are using steam, the water steam, so that they can produce silicon dioxide and the hydrogen molecules. The benefit using the wet oxidation is that the reaction time is very fast, so it can make much more oxidations rather than the dry oxidations. However, the dry oxidation has the benefit that uh, the because of reaction rate is very slow, but it can be very well grown, which means it can be grown with very dense. So the dry oxidation and wet oxidation has each benefit. When we grow the silicon dioxide is not just grows on top because of, we can see the formula, the silicon dioxide are made consuming the silicon. So when we oxidate in furnace, we have these sacrificial wafers, like dummy wafers, for the evenly deposit the reactant, the oxide or oxygen or wave water. The oxidation process is like a etching process. We inject the oxidant or reactant, and then we wait for the chemical reactions. And then for the wet oxidations, there will be a byproduct, the hydrogen molecules. The hydrogen molecules are drained out using a gas injection or ventilations. There is very important laws for describing the oxidation process in the silicon wafers. Before we oxidate, we first remove the here in native oxide. After we remove the native oxide, there will be oxygen or hydrogen. The water will be injected, the reactant, by the Fick's first law. The infiltrating particle flux are defined with the surface reaction constant, product of surface reaction rate constant, and the initial concentration of reactant or oxidant. And then if we after on the surface the oxide would be grown, then the oxide would be come in to the surface with the diffusions similar to the current density, like the formula is similar to the current density. So after all, the at the first of reactions, the reaction rate and the initial concentrations of oxidant is very important, and the oxidate rate would be similar to the uh, first order uh, equations. After that, after some times later, the diffusion coefficient is getting to be dominant. So it follows like here in parabolic uh, motions. By the consumption rate, which means the how oxide sacrifice the silicons, the rate is that the depth of silicons are 46% of the total oxide thickness. The Arrhenius plot is for important for referencing that how how fast we can react on the wafer plane. There are several factors on the oxidations. First, we can choose or dry or wet oxidation, and then the also the temperatures are very important, and the also the pressures are important because the pressures allows to infiltrate on silicon wafers faster because the oxidant concentrations gets high, and the substrate dopant can be affected on oxidations. As I said, the dry oxidations has a low on speed, but it can grow dense on the silicon wafers. However, the wet oxidations have faster reaction time, but it has lower quality. By the by these equations, the pressures are very important for the oxidation process. In the oxidation process, we would like to get lower temperatures. For the same amount of temperatures, if we have more pressures on the furnace, then the oxide thickness, we can get more dense and more grown oxidation, silicon dioxide. And it can be affected with the crystalline orientations as the as we go as we oxidate on the 111 plane, because of 111 plane has almost twice of the 100 planes dangling bond, so it is easier to penetrate the oxidant to the silicon surface. So there are a lot of arms to having a bond between them. So the oxidation rate is very high. And then the 110 plane after the 100 plane. In the amorphous, because of the silicon dioxide has a amorphous plane, so it can be a ambiguous plane on the ambiguous side. So we have to prevent those to be happened. Like here, those surface has a dangling bond, so it can be a charge can be trapped, so it can cause for a bad swing. And to prevent the contaminations on of the metals, we use chlorine containing gas when we oxidate. Using this, ions can get bond with the metals, so we can prevent those prevent the metal ions on the oxide. And there is the dopants, the effect of dopants effects in silicon dioxide. On the silicon, here is silicon surface. In the segregation coefficients means that how well in dopants can move in silicons or SiO2. For the if the coefficient is smaller than this one, that means it can be more more concentrations of dopant is in the silicon dioxide. So if we dope in the silicons, then the dopant can be get easier to move to silicon dioxide. And then if the dopant has slow diffusivity, which means it has a heavy atoms, then the dopants will be depleted on this wafer surface. And if the dopant also has a faster diffusions, like if it's light atoms, then the dopant will be drained out. So the depletions on the silicon wafers can be more enhanced. And then if the coefficient is the over 1, which means there are a lot of dopant in the silicons than the dioxide. And also if dopant has low diffusivity, like heavy metals, heavy dopants, then the dopant would gather up in the surface. Dopants are piled up near the silicon surface. But however, if it has this fast diffusion or have fast diffusivities, then the dopants would be drained out. First, the dopant will be piled up in the surface. By the diffusion, the dopants will be drained out to the silicon dioxide. By the using those segregation coefficient, there are, if we use boron as a dopant, the boron was the coefficient was below 1, and also it has slower diffusivities. So due to this, borons are moved to the silicon dioxide, so it makes this space between these oxide, so it causes these leftist it causes the path for the oxidant to the surface here, so that it can make faster oxidation rate for the growing on silicon dioxide. And then this phosphorus, if we use phosphorus, the phosphorus was this segregation coefficient was over the 1, and then the dopant as the dopant's diffusivity was low. So using this phosphorus, then the dopants would be piled up on the silicon surface. So because of the dopants are very almost very many on the surface, so it can weaken the bonding between the crystals, silicon atoms. So it causes to be a oxidant can be easily penetrate on the first beginning of the reactions. So it can easily oxidate on the at the beginning of reactions. What the boron is make faster in the during the after the slower reaction time. On the if we grow this silicon oxide on the polysilicon's like polygate, then due to the polysilicon's has polycrystalline structures, so there will be there are chunks in the surface, so there will be a discontinuity on the surface. Then the oxide will be growth with following this discontinuity. There are another problems using on the oxidation process. If we oxidate this hard masked or masked patterns, then on the silicon surface, the oxidant can be easily consumed, reacted. So on the silicon surface, on the exposed surface, then the more silicons would be consumed, then the more oxide would be on the under the surface. However, on the hard mask or masked plane, the oxidant would have to penetrate the silicon dioxide. So the reactant is moved to using these diffusions. So the less silicons are consumed, and then the oxide will not grow as exposure. The doping process is very important for in silicon fabrications, because using this like group 5 dopant and the dopant and acceptors to move intrinsic Fermi levels on the energy band diagram to make more mobile carriers. For dopings, we have two ways for dopings. First, the summer diffusions, which uses a pre-deposit dopant, and then the ion implementations, like ion similar to the ion millings. We bombard these dopant ions to the wafer surface. First, the thermal diffusions. We first pre-deposit the dopant the source of the dopant is the solid phase and also the gas phase, which has a dopant. We use also ion implantations in the diffusion, thermal diffusions, because like on the surface, we deposit ions on the surface, and then we give the thermal energies to diffuse in. We call this the drive in. There are several ways for diffusions. It's very similar to the oxidations. We first, for the solid source, we flow in the nitrogen or oxide oxygen gas, and then there are there are some both in the diffusion tube. On the boat there is a solid dopant, so blowing those on the surface, then the wafers can be doped. Like similar to the oxidations, there are also the dummy wafers. For the liquid, it is very similar to the solid way. It can also blow the gas using this with the liquid source. For the gas source, it's similar to the liquid source. And then diffusion process. Calculating the diffusion process is that similar to the on the oxide. We will use also Fick's law. For the first Fick's law, the flux was defined with the diffusivities and different concentrations gradient, or the gradient of concentrations. And for the second law, the second law is continuity equations. The difference between the concentrations is defined as the different variations between the flux between for the difference for deltas. We will simulate in two ways. First, we predispose for the predispositions, which is initial conditions is that on the wafer surface there will be plenty amount of the dopant, and then for the first time there will be no diffusions. If we using these initial conditions, if we solve for these differential equations here, then the solutions will be the error functions of the product between initial concentrations and error functions between these diffusion lengths. The reason we call this product between diffusivities and time for the diffusion lengths is that the diffusions are parameters for how fast and how fast. So if you use this for metric systems, would be centimeter squares per second, if we product time and then on get root square, then the last parameters would be centimeter only. So the product between time and diffusibility is diffusion length. So the areas of those we can define those as how many atoms in the areas. So the dimension is areas, and if we those integrate these solutions, then these outcomes would out. And then there are second solution, second scenarios, the drive-in. In the drive-in, we will define initial conditions as on the very far plane of the wafers, there are no concentrations, and for the initial time, there will be there will be already has a gradient of the concentrations, like here. So using this, and then lastly, there are no further injections of dopant, which means no diffusion flux on the in and out on the surface. There will be only there will be no source of the dopant. So the first, if we draw these arrow functions, on the arrow functions, which can be varied on the diffusion length. So if the diffusibilities are very good, then from the surface we can be penetrate or infiltrate on the surface well, and if the diffusibility is bad, which means the dopant is very heavy, then the dopant would not be penetrate well. So after that, if we drive in, then also similar to the diffusibilities. If it has good diffusibilities, then it can spread out well, which means it can be diffused well. So on the surface, the concentrations will be lowered, and then it can diffuse out on the deep side of the wafers. For the low diffusibilities, it is similar on the initial concentrations, and it can penetrate shallow. So for making the shallow gate is very shallow dot range is very important because of VT reductions. And we will define the junction depths and the net impurities concentrations. If we dope and if we drive in this dopant, then how can we define as certain point that defines N types or P types? Then there is the we call this junction depths. We can define junction depths as the impurity scale of the dopant is same as on the background doped silicons. So the effective junction doping concentration is the difference between initial concentration on the dopant and the background concentration. And the thermal budget is very important for the on the total process, because due to the summer doping, using these dopings here, using diffusion as doping is very high temperature process, is like 1,000 degrees Celsius. So it has a very disadvantage for using high temperatures process, because on the oxidation part, we used we also used thermal process, and then it can be also affect to the another process like oxidations. And then these after we dope, then we cannot go back on the process, because of it can be more diffused, so we would not get the target doping concentrations or junction depths. Also, if we like for if we process the lower temperature process after before this doping, then the silicon can be damaged, or the structures, the patterns, micro patterns can be damaged. So so using this, we have to use rapid, very high thermal process, very high temperature process we have to use, because this dopant can be diffused fast at the high temperatures, but in very short exposure times. So in annealings, we formerly used the furnace and its annealings, which uses quartz silicon dioxide furnace. Due to heat propagations, it cannot evenly propagate thermal energy evenly on the wafers. So, and also like the wet etchings, it can not control well. So we use a rapid thermal process, which uses a lamp, and then it just only need short durations. It can has better thermal control, thermal controllability, because by the furnace, different between the furnace, it can be where the temperature can get lower and faster than the furnace. However, it is not enough time for controlling this drive in or activations. It can be more drive in. We cannot, it is hard to control this diffusions process, because we cannot control these temperatures. fast. So nowadays we use this laser annealing. Using this laser annealing is it has good time controllers, so it just only need for a short time. It spikes up to the 1400 degrees Celsius for the micron scale microsecond by the for the RTPs. Then it is it has for long time for cooling down. So the laser annealing is good for making the shallow junction. And nowadays, to prevent this depletion overlap, it is very important for having shallow junctions and the more capacitance on oxide. So it is important for making shallow junctions and thinner oxide thickness. So also we need a very highly doped source strain to reduce this contact resistance by the reducing how we reduce contact resistance using highly doped source strain is that we use this tunneling on the metal semiconductor junctions. Using this ion implantation is having we can control the dose very exactly on the depth profile, and it has a lower temperature process. We can use photoresist mask, and then it has the doping is usually affected on the deposited all over the wafers. It is very important doping uniformly. So only for this prospect, it has very good uniformities that ion implantation has. However, it has very expensive. As we saw in the ion millings, it can damage the silicon lattice because of it damages the silicon. So the amorphizations can occur. The channeling and surface etchings can be occurred. The ion implantations, we first make ions using we make the dopant as a plasma ions, and then we use magnet to selectively choose the dopant ions, and then we accelerate on the acceleration tube, and we focus in the ions. And then using these scanners to vector the ions to the wafers. For the ion source, we use dopant gas, and then those makes if we make to make ions, we use this filament and ion. We generate ion using this plasma. And then on the next stage, we select these implant ions using the Lorentz force and the centrifugal force to select the certain dopant ions and prevent the another byproduct ions. And then the scanning systems. Using this electrical field, we use this we dope the uh, we move the beam, so like scanners. We first dope here, and then we dope this dopant in the wafers using this electrostatic scanning, like using vectoring the ion beam using electric field, and then mechanical scanning. We also move the wafers. And how can we know how much those are implanted on the wafer? Is that the using this Faraday cup in the wafer holders, we punch the small hole in the wafer holders, then the ion beam would be up here, then the ions would be accumulated in Faraday cup. So those ions make the those ions are charged, so it produces current. So by measuring this current generated by the ions, we can calculate this area dose. And then if we have the area dose, which means centimeters minus 2, how can we make area dose is that if we have 10 of them, then we scale root and the cubic uh, cubic of them. And for the implantings, there will be the ions can be penetrate through the silicon lattice, then the collisions would be happens. There are two kinds of collisions. Bumpering. First, that nuclear stopping. The dopant ions are collide with the silicon atoms, so it can collide with nucleus of the silicon wafers. So those are scattered, the dopant and the silicon wafers, silicon atoms, and it can cause the structural damage on the lattice. And then the electronic stopping. The electronic stopping is that the accelerated ions can get through this lattice, and then due to the electrical force on the electrical attracting force between the electrons on the silicon and the dopant ions. So it makes the small but very it makes more electric field, so it slow down the ions. So the electron stoppings occurred in highest velocity. After we go through the silicon lattice, the ion velocity would be high, so the velocity would be get lowered due to electronic stopping. After that, after we slow down enough, then the nuclear stopping happens because because it is so slow. So the probability of colliding with nuclei is much higher than when fast. The whether we can define the dopant this penetration depth as the uh, the ions energies, accelerated energies, and the ions mass. And then if we have more accelerated energies, then it can be get deeper, and then also you can spread it out because of the nucleus stopping. And also if the diffusivity is good, like if the molecules have ion has light atoms, then it can go deep. Also, it can spread out more likely. For the heavier materials, then it cannot spread out, and also it cannot be go deep. And then there is a mean projected range is that as this dopant concentrations follows these Gaussian distributions, so the mean projected range is very important. And then the junction depths. So as this dopant concentration follows the Gaussian distributions, so we can calculate this using standard deviations. If by the 1 sigma, the 68% of the dopant are located, and for the 2 sigmas, almost 60-70% of the atoms dopants are located. After this second sigma, we can say 3 sigma, we can say almost all of the injected dopants are located. For the selective implantation is very important. We will define as the mask can be masked using these Gaussian distributions. If the concentration of certain point is here, let's say x0, then if the concentration on this selected point is bigger than the 10 times of less than the 10 times of background concentrations, then we can say it is masked. It's blocked by the mask. And then the junction depth. The junction depth is defined as the standard deviations and the mean projected range. If we implant several times using different energies, if we by using this multiple doping, we can make uniformly distributed concentrations. And then the channelings. The channelings occurs due to the ions go through these holes within the lattice. So to prevent these, we can tilt the silicon wafers, right? If we have beam, ion beams, then we tilt these ion wafers like here. If we tilt these ions, then first the junction depth is get lowered. However, this tilting has problems. If we use tiltings, then the shadowing effect occurs. Like here, the ion beams are very anisotropic. So if we give tilt angle to the beam, then the ion beams, certain ion beams will be blocked by the polysilicon or mask. So for the 3D structures, this FinFET, it can be overcome, like doping in several angles. However, it can cause this overlap here. So overlap doping. So it can cause more unwanted, more doping concentrations. However, this method has the limitations because of this. For higher, more narrowed fins or higher fins. And then the lattice damage. The lattice damage is caused by accelerated ions. For the lightweighted ions it can be more penetrate. So the damage is due to nucleus stoppings. So the heavy ions have more damage on the surface. Like for the ion millings, the heavy ions can etch out the silicon surface, like here. So it makes the uneven surface between the surface and making these amorphous silicons. In the alpha Si, we can cure the recrystallizations or on using these annealings. Like here, we can first we ion implantate, and then the amorphous silicons occurs, and then using these annealings, we can restore the fin shape. Here, this activation annealings. However, this using the activation annealings can make these defected areas. So nowadays we use this heated plate, hot plate, using for heating the silicon layer when we implant. Then it also has the implant. After the implant, also the defect occurs. However, if we cure after all the annealings, the better crystallizations occurs here. Nowadays we use this PLAD, which means plasma doping. We first pre-deposit the dopant, and then also we use the boron radicals like plasmas for evenly dope. But nowadays, we rarely dope on the fins channels because it has very small areas, very small volumes. So if we dope using these doping concentrations, then the only 10 dopants have to exist in the channels. However, we cannot control this well, these atoms, each atoms. So if the the concentrations each fins can be differed, so it can cause the pretty roll off, bad swings, and then the capacitance